I'm going to talk about RavenDB 4.0 before 3.5 was even released. The reason that I do that is that for the past 6 months, we've been primarily working on 4.0, and working on 3.5 was primarily in stabilization and closing all of the taxes that you need to do before you can actually do a release. What you see here is not a release schedule. If you try to look at this as a release schedule, it will look very, very strange. Instead, I pulled this data from the actual work that we are doing. So you can see here that by the time we actually was working on 2.5 beta, we already start working on the 3.0 beta. And that's actually one of the nice things with having larger teams, that we can work on more things in parallel. So roughly speaking, those are the dates around here. So, sorry, around here. This is where we are actually stopped working on the release of 3.5. That already happened, by the way. So the release of 3.5 right now, the only thing that we are doing right now is brushing off all of the dust and making sure that all of the taxes are paid. Taxes are things like making sure the UI is consistent across everything, making sure that we have the appropriate documentation, making sure that the stabilization, performance, longevity tests are running and are passing properly. And for the past almost 9 months or so, we have been focusing primarily on what do we want to do in 4.0. And we started doing that by getting into severe depression. And the problem is very simple. I mentioned yesterday that one of our primary forms of feedback from customers is this is broken, this is slow, this is doing something they didn't expect. And in many cases, what happened, so that sounds really, really bad, right? The problem is that most of the time, when a customer actually talks to us, they only talk to us if there is something bad. In the entire history of RavenDB, there has been 5 people who wrote, oh, I had a great experience with RavenDB. For everyone else, it just works and they don't even understand the level of effort involved in just getting there. I was speaking with Jonathan yesterday, and he told me that one of his guys never worked with a relational database. So for those kind of guys, all of the things that we are speaking about, things like, okay, let's do automatic index analysis, let's have the database automatically adjust to what you're doing. Those are things that are just there, and obviously you're going to do that. And when I explain to them about, oh, this is awesome, it sounds like, yes, Grandpa, I know that you walked in the snow to school 16-mile uphill both ways. So, but honestly, a lot of our time is spent processing users and customers that talk to us about the server, and we gather quite a lot of feedback around problematic areas in the code. And at some point, I just got really, really frustrated, because right now the RavenDB code base is over 1 million lines of code. According to standard industry metrics, if you put one person to write the RavenDB code base, it would take them about half a millennium, so about 592 years. So that means that it's actually quite hard to go and make drastic changes. And at the same time, we made a lot of decisions very early on that made a lot of sense at the time, but now we wish that we would make them differently. So the question here, we started working on RavenDB in 2008. We went to production in 2010, and since then we have over half a decade of experience in actually running RavenDB in production. And just to give you some idea, running RavenDB in production, Rodrigo story aתמול about the crappy machines. We have a customer in Germany who run a point of sale system in grocery stores. And their standard machine there is Celeron 667 with 512 megabytes of memory running Windows XP that I'm pretty sure hasn't been updated since the release. So that's on the low end. We have users who keep talking to us about, okay, I want to run on Amazon micro instance, and I want it to be fast and easy and responsive. And we also have, we had a bug report several years back where someone says, I went and got this machine with 64 gigabytes of RAM, with 1 terabyte of SSD drives, 32 cores, and RavenDB is just sitting there processing, and it only takes about 6 gigabytes of memory. I'm like, okay, I understand that you're upset about that. What is the response time that you have here? Oh, all of the requests complete in under 10 milliseconds. I'm like, do you want me just to allocate a big buffer? But that was several years ago. Now we have users that are running on machine from half a terabyte of memory and 64 plus cores and just crazy stuff, and we need to adjust to all of those. We also need to adjust to a crappy machine that don't tell us that they are crappy. So if you go and look at a network I/O, the I/O on Azure, stuff like that, that makes things a lot more complex because you have a lot of CPU, you have a lot of memory, and your I/O is just out of proportion to the machine that you have. We have a lot of code dedicated to managing that. We have a lot of code that run heuristics, analysis on the machine, all bunch of stuff just to get things working. Another thing that we notice is that in many cases, our cost isn't directly proportional to what we are doing, but directly proportional to what the .NET framework is doing on our behalf. So one of our problems is that a certain workload can trigger a lot of GC collections. And effectively, the customer calls us and says, we're running on high CPU and slow throughput, and now we need to figure out why. The last case that was there took us 2 days to figure out that the I/O system would basically lie to us. On that particular set of machines, if you issue a read request for a large document being several megabytes, this would complete very quickly. If you issue a read request for a small document, some kilobytes, then it would take far, far longer. So there wasn't this proportional between the size of the read request and the amount of time it would process. I don't actually know why. The actual system was some sort of SAN with a quality of service settings, apparently. And basically, it killed our heuristics. That means that we would load too much stuff into memory and wouldn't be able to release it quickly and a whole bunch of stuff like that. And that was just really frustrating because now you have to make modification to the heuristics to handle this specific scenario, and also now need to test all of the other scenarios that we have. We have a machine at our office that we plug hard disks to. And I actually went and got old machines that I have, like from 2006 and stuff like that. So we have a 10-year-old 5200 RPM hard disk that we use to simulate those kind of things. And all bunch of stuff like that, just to be able to make sure how everything works and how it works with actual hardware, not just with, simulating flakiness using some sort of virtual drive. So what we decided to do, we decided that for 4.0, we are going to do a major pivot. We're going to say, okay, let's analyze where is it painful, and let's accept the fact that we're going to change that. On the cards here, you have the design document for 4.0. Again, this is an internal design document, so there are some things that are not going to be there. So some things that we talked about here are not going to be in the release. Some things are going to be there that have changed. But the idea here is that to give you a lot of insight into what we are talking about and what we are thinking. When we started looking at the kind of things that are problematic for us, what we realized is that in almost all cases, the problem was when we have something that we couldn't control, something that was out of our purview, something that when there is an issue here, we couldn't fix it. At the same time, having access to something to fix it doesn't mean that it's easy to do. So we wanted to say, okay, let's start from scratch. Now we have all of this experience in running RavenDB. Let's assume that we don't have RavenDB. We don't have any existing user base, we don't have nothing. What would we do differently? And we sat down with that, we built the ideal vision of the database. Then we said, okay, now that we have this ideal vision of the database, what are we actually going to do given that we actually have users deployed? And we have, Rodrigo with 500,000 machines running RavenDB. He's not going to be able to just, oh no, let's just update everything in one go. So those are the core design principles that we have, and primarily among them is the notion that we can't handle complexity. There are parts in the RavenDB code base right now that are currently understood by 3 people on our team. The other guys, when they go there, they go, okay, now let's see the code. If you care about that things like the MapReduce optimizations, so there's a lot of stuff around that is incredibly complex, both because the actual implementation is complex, and in order to make it perform fast, we have to do some, again, crazy heuristics around a lot of those sort of things. Federico actually ran into problems with that when his MapReduce index crossed the 1 billion points. So 1 billion things being indexed in the MapReduce index, that starts to show some major slowdowns, and we fixed that to a certain degree. But there is a limit to how much you can fix things without actually laying down the law and starting from scratch. So why is it so important that complexity is not maintainable? Because now we have a large team. Now we have a lot of people working on all sorts of different parts of the code. And we don't really like it that there are certain parts of the code that, okay, if I give them to Arek or Grisha, that's going to take 2 days. If I give them to Idan is one of our new guys, we hired him like 3 months ago, it's going to take him a week. Now, admittedly, the different skills level and different knowledge are going to play a factor, but we want to have, okay, now we have a common design principles and common behavior across the board. And if we have to choose between simplicity and complexity, we will always choose simplicity unless the evidence is overwhelming that you can support that. Another issue is that we must control the stack. I will give you some example further on about what's the kind of thing that we can do where we control everything. Another primary goal is that we must be faster. So I want to come to you in about a year and tell you, look, here is RavenDB 4.0. You can upgrade to that. It's going to be somewhat different. You need to, that's a major version, that's a big release, and you're going to get that amount of better performance. Just that. Just to give you some numbers, we are currently, the last time that we ran proper performance stats, we were able to process over 100,000 requests per second on a single node. Our goal is to go higher than that. But that was in RC1, CoreCLR RC1, and we moved to RC2, and we haven't been able to run the appropriate performance testing system because it just happened last week. But that's the kind of thing that we're talking. We're talking about the ability to have a single server really kick ass and be able to perform really nicely. And something else that is important, there are certain areas in the code that are painful. They are painful for us in terms of having to maintain them. They're painful for users. We work a lot with RavenHQ to find where there are operational issues. I don't know if anyone actually noticed that. A while ago, we moved a configuration value from the client side to the server side. That was what should be the failover behavior in a replica cluster. And it used to be that value was defined on the client. RavenHQ had a lot of cases where people would just use their own defaults. And they had a cluster of servers, and one server went down because of outage, or you have to run patches. All traffic is supposed to run to the second server, but the client wasn't configured properly. So that's something that we work with them to add that, and now at the RavenHQ level, they can set it up, and if there is some sort of an issue, this transparently fell over, and the client doesn't need to do that. This is an example of something that we're going to do more, move more responsibility from the client code to the server, so the admin can change that on the fly. Other things are related to taking upon ourselves all of that complexity. Instead, we're going to set things up so we don't have to deal with that, and I will explain about that in a second. Rodrigo said yesterday that he doesn't like ECENT. To be fair, ECENT is a wonderful tool. We learn a lot from that, but it's really easy for us today to point to multiple different issues there. When we have a problem with ECENT, then if we can't work around that, that means that we have to do escalation to Microsoft, work with them, have a hotfix patch release, send that to all of our customers, a whole bunch of trouble that makes it very hard for us to iterate quickly. Other issues is that it doesn't run on Linux, and that's something that we really want to be able to do. And most importantly, for the 4.0 release, the ECENT gives me a high level, it's funny, it gives me a high level API over low level storage, which sounds like, sounds stupid saying that. But we said that we're going to use Voron, and the major reason that Voron is so important, besides Linux and we can do that, the major reason that this is important is that we are now able to make very low-level storage decisions based on what we actually need to do. The MapReduce implementation in 4.0 is 7 orders of magnitude simpler because of Voron, because we're able to utilize the internal structure there to make things much, much simpler. And finally, Voron is purely based around memory mapped files. Why is that important? It's important because it means that during steady state operation, we can run and process requests and do pretty much everything that we need to do without ever making a system call. That means that we don't have to switch to kernel space. That means that we don't have to pay that additional cost. It's much, much, much faster. It also means that we are more efficient because there are only one copy of the data in memory instead of one in the page cache of the operating system, one in our user space memory, and all sorts of stuff like that. This is JSON. I assume that you're familiar with that. If not, you're in the wrong conference. Here's the problem. JSON is an awesome format, and it has a very interesting property. It's a streaming format. What does it mean that it's a streaming format? If I ask a computer to tell me what is the home phone number of John, what does it need to do? What it needs to do is to read throughout this document, find this home, and then give me the number. So that doesn't seem like that would be such a bad idea. The problem that we have is that that means that every time that we need to do anything to a document, we need to parse it. Think about what it means when we need to load a document to send it to the client. You ask me, give me user/1, and I need to give it to you. Internally inside RavenDB, the following things happen. We read the document from disk, and now we get a stream of bytes. We parse that into a JSON object, and then we take that JSON object and we write it to the network. And that sounds relatively stupid, because we have string of bytes and we end up writing a string of bytes. And they are roughly the same, but they are not the same. That's why we have to create the .NET object in the middle. We pay multiple times here. We pay the cost of parsing. We pay the cost of writing the JSON to the network. And most importantly, we pay the cost of actually creating all of those .NET objects in memory. Why is this important? It's important because when we create all of those .NET objects in memory, at some point the GC is going to have to intervene. It's going to say, okay, I need to clean all of that up. And now, what I just said was true and false at the same time, because this isn't actually how it works with RavenDB. Because when you load the document, you don't actually go to the disk. You go to a document level cache, and typically we'll find your documents inside that cache already materialized as a .NET object. And if it's not there, you're going to hit the page cache. So you don't have to hit the disk, but now you have to just parse it. And if you didn't find it on both, only then will you actually go to the actual disk and find that. And in most cases, you will hit the page cache of the operating system. And if you think this is complex, wait, that's one of the simplest scenarios that we have to deal with. It also means that during indexing, let's say that I have users document where each one of them is about 16 kilobyte in size. And I want to index them based on the name and the email. That means that I have to read the entire document, parse the entire 16 kilobyte into memory, create an object, index that, just use the two fields that I need, and then throw it away. That creates a lot of pressure on the GC. That creates a lot of pressure in terms of CPU time just to do all of this parsing. And that's something is the blit-able format. The term blit-able is a term that is typically used in graphics programming. It refers to taking a part of a background buffer and passing that to the video memory in one shot. I hate that name. We're just unable to find any other better name to do that. So the whole idea with blit-able is that we don't store JSON as a JSON string anymore. Instead, we have a format that gives us the following options. One, it gives us full random access throughout the document. It means that all of the memory is actually one block of unmanaged memory. So if you imagine how it works with a JSON object, you have a dictionary, and then you have a string, and then you have the array, and then you have the string, and all of that is typically spread over in multiple different .NET objects, and you don't have any locality of reference. With the blit-able format, we allocate some memory, and all of the data is there. So accessing that document, we don't have to jump around in memory. That plays very well with the caching architecture at the CPU level. But most importantly, it means that we don't have to do any work once the document has been loaded. And how do we load the document? We just need to have access to that buffer. Remember that I told you that Voron uses memory map files? So now the cost of loading a document means, okay, given this document, given this document ID, give me the position inside the memory map buffer where this document resides, and give me its size. Based on those two numbers, now I have this, and I have the pointer that points here, and now I know exactly what to do. All access from this point on is based on pointer arithmetic. So if I'm asking you, give me the phone numbers, I know based on the structure that I need to jump here, and here is the phone number that I care about. And just that thing, just these two changes. Use Voron and memory map files and use the blit-able format. Change the entire ballgame as far as we are concerned. Why? Because now the cost of accessing a document is the cost of addressing that memory map file. And you can see here all of the things that we don't have to deal with. Accessing a document now has 0 managed allocations. Actually, that's a lie. We need to allocate one class that holds the pointer and the size, and that's the class that actually knows how to parse that value. So if I need to go to a phone numbers type, it knows how to process that binary data. So instead of having to allocate 16 kilobytes of a managed memory, now I need to allocate 16 bytes. That's roughly the size of this object, because it just stores a couple of pointers. That means that we don't no longer have to have prefetching. Prefetching is critical for I/O operations. But most of the time, prefetching will actually spend in getting the data and storing them, and that actually led to a problem. Because if we have a prefetching queue that we needed to feed to the indexes, that means that we need to materialize a lot of .NET objects, typically in the order of 64K to 128K. And those objects are going to reside in memory, wait for the current indexing batch to complete. The problem is that indexing generates a lot of garbage memory because they run through everything, and then they, all of the memory consumed by indexing is just garbage, so that triggers a collection. When that triggers a collection, then the prefetch memory, which is still being held because we're just going to use that, is going to be upgraded to the next generation. So that one is going to be collected much later, and that gives us a lot of memory pressure. The whole reason that we have index batches in the first place is that we didn't want to have multiple copies of the data being processed by indexes, by different indexes at the same time. But now we don't have that. We have all of the data, all of the indexes are looking at the same data, which is memory mapped and not under the control of the GC. And now we can have different indexes running on in different speeds, and we don't have to coordinate between them. So that's huge, because that means that a lot of the complexity around that just goes away. We don't need to handle caching of the data inside the RavenDB process, because again, there is nothing to cache. And again, the managed allocation is greatly reduced. So all of that. Now, think about what this means. So far, we up until for all indexes need to run in batches. If we don't need to run them in batches, that means that they can run independently. And if they run independently, that means that I don't need to do any sort of thread pooling. I don't need to try to do manual parallelization of the work. I can just say something much, much simpler. An index is a thread. And that thread is going to basically index everything in the collection that it cares about. And that means in turn that they get several very interesting properties. To start with, now I don't need to care if I have an index on users and you modify an order. I immediately know that this index isn't involved. I don't need to do anything. That thread doesn't even wake up. It continues sleeping until a user is being modified. It also means that you can now tell me, this is an extremely important index. I want you to prioritize that higher than all other indexes. And I can do that. I can also say, okay, indexing work I'm going to dedicate 6 cores just for indexes, and I'm going to process requests on the other 6 cores. So I don't have fights between indexing threads and request processing threads. Overall, the indexing code now looks something like that. Give me all documents in this collection after etag X, index them, and do that in a loop. If there is nothing to do, I'm going to wait until a document in my collection has been changed, then I'm going to start running that again. We deleted about 80% of the indexing code that we had to deal with. Just gone, none of them. Now, remember when I told you that complexity hinders maintainability? One of the things that we routinely do in Voron now is set things up so we play to the strength of the operating system. So we don't use caching anymore, but we actually do have caching. We have caching because we now rely on the kernel's page cache to make sure that everything that we access is actually resident in memory, in physical memory. And we had in 3.0 we have a large section of code and heuristics and behavior around how do I index new documents, because I already have the documents in a .NET as a .NET object, and I don't need to read it, to write it to this and then read it back again and pay the price again. So I have a queue of newly arriving documents that I'm keeping in memory so I can index them. But what happens if I'm under memory pressure? So I need to handle the memory pressure by purging the incoming documents queue. So otherwise I might might run out of memory. So there's a lot of behaviors around that. With what we have now, a newly arriving document is going to be in memory. Why? Because we just wrote it, so the operating system is going to consider to be hot property. What's going to happen if there is a memory pressure? The operating system is going to start paging things out to the data file, which is precisely what I wanted to do. So we spend a lot of time setting things up in such manner to make sure that things happen the right way without us having to write all of the code and manage all of that manually. Okay, so what we have now, this is how we store things on disk. In 3.0, we effectively store all of the documents inside the same physical space. That's why if you modify an index, if you modify a document on any collection, all indexes are going to become stale. In 3.0 and 3.5, we have changed things so we are smarter about that, but just by modifying in-memory structure. It's not because when you write a document, we know where it's going to go, so we can be slightly smarter about this. It doesn't help if you need to create a new document, a new index on a large collection, on a large database. We have some optimization around that with pre-computed indexes, homers, or stuff like that, but again, complex code that we have to write and maintain and have heuristics around. What we've done here, we have split things up, so every collection is physically separated inside the data file. And what you see here, those are the etags. And now for every collection, I actually have a different index for all of its etags. So an index, okay, we have a problem. We use the same terms twice. We have storage index, which is what actually is used by Voron to internally manage the data inside the data file. And we have a RavenDB index, which is what you're familiar with Lucene and everything. So A storage index allows me to query all of the users by running through them in itag order. The problem here is that this is only per collection. So this is great for RavenDB index that need to say, okay, give me all of the users. I only care about the users. That means that in a large database, on a large collection, we will only touch the relevant things and we'll be able to complete indexing much, much faster. On the other hand, there are many, many cases where I actually need to go over all documents, period. That's relevant for things like replication. That's relevant for things like import, export, incremental backups, those sort of things. So what we actually have, we have this team which goes over all of the documents. And now when I need to iterate over documents, I have the ability to choose. Either do it on a per collection basis or do it over all documents at once. This seems like a trivial thing, and it looks very simple here. That's one of the main things that we could do in Voron and couldn't do with anything else. Because internally, think about it, if we're talking about a relational database, this is an index, a storage index that covers multiple tables in a relational database. That's not something that is available unless you are able to do some very low-level changes to the way the storage is architected, and there are all sorts of optimization at that level to how we access things, how we operate on those levels. Just to give you some idea, typical documents in RavenDB are in the multiple kilobyte ranges. When I'm iterating over something like this, it's especially if I'm doing a new index, so I'm going to have to start touching documents that haven't been touched in a while. Then what we can do now, we are starting the iteration. We're going to say, okay, let's take a bunch of 256 documents, for example, and ask the operating system to preload them to memory by issuing the optimal number of requests. In Windows, this is used by the prefetch virtual memory syscall. In Linux, this is used the madvice call with will need. And that basically gives, now we're able to give the operating system hints about the kind of thing that we're going to do. And when we're indexing, that means that by the time that we index, we already have that same behavior. The data is hot and in memory. And this is relevant for both new indexes or, I add a new replication target. So I need to start pushing things there. Okay, so that's what I basically said. Very important is that because we only cover the collection for the index, if the collection hasn't been modified, the index doesn't need to do anything. Now, status checks are explicitly per collection because we can check here what is the last etag for this collection, and it's extremely cheap and we don't have to do anything around that. Every index would be a separate thread. If I modify a user, all of the user indexed thread are going to run. All of the other users just don't have any reason to run, so they just stay quiet and don't do anything else. That also means something extremely important. It means that we have accountability. What does it mean, accountability? Let's say that you have a high memory usage. We can now, very easily, narrow down what is the piece of code that is causing the issue and what is the exact index that is causing that, because we can break into we can look at the threads that are running. We can see, okay, this thread is using a lot of memory. This thread is using a lot of CPU. And we can see, okay, this specific thread is for users by activity date over the last period of time, or whatever Federico does with the indexing. And that gives us much better tools to actually understand and figure out what's going on, to the point where we are now able to go to the admin and tell him, okay, here are the costs that you have per index. This is how much CPU they take, this is how much memory, this is how much IO that was generated, all of that. Yeah. Okay, so the next thing is with Lucene. Lucene is a great search engine library that we hate. The reason that we hate is that we have been in the guts of Lucene quite a lot. I've tried to rewrite something that would fill the same role as Lucene multiple times. I have successfully made something that has less feature than Lucene, takes more memory, is slower, and uses more disk space. It's funny, right? So we're not going to use that. That was Corax. We have run multiple tests on that. We know what needs to be done. The scope of the work is very large. So this is still, a to-do item somewhere. I don't know if we ever get that. But we knew that there are certain things in Lucene that we couldn't live with. Primarily among them was the reliability. Lucene is not reliable because of the way Lucene writes to the file. If tomorrow I'm going to the workshop, if we have time and if you like that, I can go into depth about how we actually get acidity. How do we get the fact that if you pull the plug on the machine, Voron ensures that the data is never going to be lost, that the transaction is either committed or not there at all. The way Lucene does that, they cannot get this ever. And what ended up happening was that we said, okay, Lucene isn't reliable, but Voron is. So let's get both of them and get them together. So now in 4, all of the Lucene indexes are actually stored inside Voron. They're stored in a relatively strange manner because we aren't storing them as you would store them inside the relational database or stuff like that. What we're actually doing, we are storing in a way that matches the access pattern that Lucene uses. So effectively, this becomes a memory map file as far as Lucene is concerned, and the access times are greatly reduced. That gives us, again, reliability in the case of that. That also means that we can push all of the information about an index to that particular Voron directory. That means that right now, deleting an index is expensive because we have a lot of information that we keep around index. Load document, map result, all sorts of stuff like that we need to track. And when you delete that index, we need to go and clear out all of those things. With 4, the idea here is that all of that information is stored in the actual index data. Again, persistent, durable, ACID, and all of that. When you want to delete an index, close that index, delete that directory, and you're done. That means that our cost now became an O1 operation to delete an index. There is also another issue here. Voron in 3.x is actually a multi-threaded database. You can run multiple concurrent transactions at the same time. In 4, we decided that this is too complex, and we changed Voron to be a single writer multi-reader system. What does it mean? It means that at any point in time, only a single thread can write to a Voron database. A RavenDB database is actually composed of multiple VoronDB databases. We actually need to find better terms for that. The internal terms that we use is that we have a Voron storage engine or storage environment, and we have a database that manages multiple of them. So for example, documents are stored as one Voron directory. Index would be an index would be a different Voron directory, and write transactions can happen on the index and the documents in parallel. So we basically made the decision that we want to make things much, much easier to ourselves. In 3.0, everything is, all of the information, everything sits on the same storage environment, on the same directory effectively. And we run into complex race conditions that we have to deal with. So all of them are dealt with, but again, we don't want to have that complexity in our code base, because we look at the code and we see this, something that looks very strange, and it's coordinate with this other thing that needs to handle a whole bunch of stuff like that. Load document, for example, in order to properly handle that with appropriate rest conditions, we have to do a whole bunch of song and dance between a read transaction on the indexes, write transaction on the documents, and none of them, or both of them are trying to write and read from different places, and you can just miss everything and miss the update. So we had to handle that explicitly. Without having that, with having, okay, every piece of code owns the write lock for the particular data that you need, then we have a much simpler model. Because effectively we just go in a loop and says, okay, let's start doing our processes. If we need to read from something else, we accept the fact that we may read information that has already been modified. Because we start a read transaction, and while we're in the read transaction, we don't see stuff that happened after we started the read transaction. So we finish the loop and start a new read transaction, etc., etc. It's a much simpler programming model, and it's something that we see across the board in every piece of RavenDB that we did that just tremendously simplify our life. CoreCLR. We've been trying to get RavenDB to run on Linux for the past 4 years or so. Just to give you some idea, we hired special consultants to do that. We actually, at some point, about a year and a half ago, we hired a guy who is a Linux expert, specifically for the task of porting RavenDB to Linux. Part of the reason that we built Voron in the first place was I want to be able to run on Linux. For years. We couldn't do that on Mono. Mono is just, it's 15 years old now, and it's not suitable for running production applications that are not desktop stuff. If you try to build real applications, RavenDB, you run into all sorts of interesting issues. Interesting issues such as the GC will try to follow a pointer to a deallocated memory and crash. That was a lot of fun to try to figure that one out. So it took us, I think, like 3 months to move RavenDB to the point where we can run it on Linux, under the CoreCLR, and we had problems. We had severe problems at some point, and they were so much fun because you weren't fighting the framework. We found lots of framework bugs, but that's, fixable. But everything just worked. It was vastly different experience. I really, really like the experience with the CoreCLR. But we made the decision, okay, we're going to run on Linux, we're going to run on the CoreCLR, we're going to see and we're going to also make all of the changes that I talked about. We're going to do that by porting the code. So it's not just copying and pasting. A good example would be SQL replication. SQL replication works in one way in 3.0, and a large piece of the code has been copied from 3.0 with very little changes. How we write to the relational database, for example. But in 4.0, SQL replication works based on every SQL replication that you define would be a separate thread working on the appropriate collections, and it knows how to access the documents in the right fashion. And again, that loop that I described that goes over and everything, and that simplified the amount of code that you have to write to actually do the work tremendously. And this is something that I actually have to insist with some of the guys in the office. Two of my guys keep trying to write the whole thing, three of my guys actually, keep trying to write the whole thing at one shot. As in, I know what we need to do, I know that we need to make it fast and correct, and we have like 15 different design principles that we need to balance about reducing manager allocation, making sure that we use the algorithm, all sorts of stuff like that. And I try to write it all at the same time. And it's incredibly hard. So I keep having to dumb down the requests. Okay, you don't get to make it run fast. You just need to give me a draft of the code. And I want you to draft the code so I know this is stupid. Feel free to say this is stupid. But make it run, and then it's going to not work. I know that it's going to not work, that's okay. But now we have the chance to iterate over how some of these things go. A trivial example would be authentication. Authentication in 3.0 requires us to do 3 network round trips with 3 different HTTP requests. In 4.0, we do that in a single WebSocket session, and that simplified the amount of state that we need to handle, the amount of complexity that has to happen. But it took like 3 hours before the guy writing the code actually says, I can't write it all at once. He tried to write it all at once, like, okay, no. Narrow the focus, narrow the focus, narrow the focus. Okay, we got it. Now we know how to read and write WebSockets at that level. Let's skip it to actually do the authentication. And then, okay, now let's run it and see how fast it goes. And let's run it under the profiler and see how fast it goes. And typically, we spend 1.5 time on the profiler and optimizations after a feature is complete, just to make sure that this is faster. She spent the last 2 months just building a benchmark code and benchmarking various parts of RavenDB and throwing that into our CI system. So now we have visibility on every build, not just when we do the stable and performance testing, on little features. So now I can tell you that doing authentication takes that much time, and we can handle that many authentication per second on this build, and then graph it over time, things like that. So this is Ubuntu 1.4. So this is Ubuntu 1.14, so 14.04. I tried doing that on 16.06 or whatever, and for some reason it didn't work. The CoreCLR isn't supported yet or something like that. But what you see here is actually RavenDB with me. This is RavenDB running on Linux. And now I'm going to run it. And this is RavenDB 4.0 running Voron on top of CoreCLR with Kestrel, compiling for some time. So this is a virtual machine, and now we have this. And here we are accessing the local machine. Is it visible? Can you see that? We're running on Linux, and we can do things like and now let's do another one. Firefox on Linux is different key binding, and it drives me crazy. And now I can do things like and the nice thing about this is that, okay, So what you can see here is that here is me, and here is the actual user, and everything works. As you can note, the UI doesn't look very different from 3.0, primarily because we have done very little work on that. I think that last week I talked with one of our UI guys and told him, okay, I need the studio to work on 4.0, copy everything from 3.5 to 4.0, just make it work. I just need to be able to demo it here. There is still a lot of plans of doing major studio work, but that's the idea. On the cards that you have, there is a build for RavenDB for Linux. You can throw that in and see that. One of the things that we're waiting for is to see the CoreCLR running on ARM, at which point we're going to put RavenDB on Raspberry Pis. And the whole idea, yeah, we have actually tested that. It works. The problem is that the CoreCLR currently can't run stable on the ARM. Once we have that, we are literally going to give you this machine, and that would be a RavenDB server. Plug in the power, plug in the network, and you have a RavenDB server. It's not going to be a very fast one, but it's going to be there. Yeah. And maybe Rodrigo can upgrade to that. Probably will be cheaper. Anyway, so so far I talked a lot about indexes and stuff like that, but in CLR, in the CoreCLR RC1, we had a problem. We couldn't do dynamic loading of assemblies from code that we dynamically compiled. If that means nothing to you, that's okay. Effectively, that meant that we couldn't write indexes, because our indexing code relies on the fact that we take your link statement, dynamically compile that, do a whole bunch of really evil things to that, compile that, load the assembly, and then start executing that. We couldn't do that in RC1. They kept promising that this would happen, but you know that the release slipped. So we're stuck with not doing anything for indexing. That was sort of not something that was acceptable. So we decided to just implement auto indexes. Now, what is an auto index? Auto index basically says this: on the user's collection, I want you to index the name property and the email is analyzed. And that leads to some really interesting implementation, because effectively we have the same index definition that does, given an index, it gives me the list of fields to index, but instead of executing link, we can just get it directly. So that gives us actually much more efficient code path to execute. We don't need to execute the link. We don't need to materialize the .NET object. We can do the whole pipeline through, without doing a lot of work. So that's great. And that means that we now have auto indexes in 4.0, as you saw. And let me show you us running on RavenDB in Windows. We run on Windows now, yay. It's amazing. When I was building this, demo, there are certain things that don't work on 4 yet. For example, Smuggler, and it was so incredibly frustrating. And then I realized, yeah, that was most people using other databases feel like. Okay, so there is a bug in the UI, but really? I call it RavenDB, call it name. Okay, so there is some sort of bug here that we need to fix. Let me see. Again, I'm not even going to call it stable. Here we go. And now you can see that we find the right thing, and here is the find the right thing, here is the information, everything works. The UI is sort of crappy and doesn't work in many cases. That's okay, we'll deal with that. So something happened. RC was released last week. Pavel in the back has worked feverishly to get us a static indexes. So now we have this, and we can do things like I need to decrease the size. Which effectively does the same thing as the auto index, but as a proof of concept, it shows that this can be made to work. If the UI would work, that would be nice. Here we go. So we still have quite a lot of things to do for static indexes, but the thing that stopped us are fixed. That means that in the next short while, we're going to have transformers again. We're going to have more complex indexes and stuff like that. Unfortunately, the team handling most of the indexing stuff is in Poland, and they did the auto indexes stuff. And then I was just sitting there saying, okay, we can't proceed because we're missing this feature in the CoreCLR. What am I going to do? What am I going to do? So without discussing that with anyone, they decided that they're going to implement MapReduce auto indexes. And this is what they got. And as you can see, now if you run this on 4.0, this will actually work and give you the appropriate results. So now you don't need to manually define MapReduce indexes for most scenarios. It just works for you. And the fun thing is that this is one of the things that happen if the team just go crazy and build stuff like that. Because I'm looking at the commits and suddenly, we never talked about this feature. But Arek, the guy who implemented that, probably spent like a day or two, and suddenly we had that. So I'm really loving that. So we actually have support for quite complex MapReduce operations. So and in Voron, I think that's going to dramatically simplify the life of pretty much everyone. For fun, even though this looks like this is actually using the whole usual MapReduce infrastructure. Actually much better, we touch it in a bit. But the whole idea is that when you query that, you're not actually running any computation. You hit in the pre-computed disk, and you're able to handle that very, very quickly. So all of the usual benefits of auto indexes with the learning on the fly and stuff like that are going to happen for MapReduce indexes as well. And now you're going to have something that just learns for those kind of things. And if you have complex queries and stuff like that, they're going to benefit from that at effectively zero work. One of the things that I spoke with the RavenHQ guys yesterday was that apparently there are people who use RavenDB and never knew that there was something called a static index. And pretty much people run into that when they try to do something that the indexes explicitly forbid you to do. Computation during index, group by, stuff like that. So now we're going to make the life of the RavenHQ guys even more complicated. We can do so much more. Now let's talk about MapReduce. This is what MapReduce looks like in theory. This is what it looks like in practice in 3.0. The problem here is that we do persistent time-dilated MapReduce, which is a term I just invented. But basically, the whole idea is that whenever you modify something in your documents, the MapReduce is going to reduce it again with some of the other results that were previously computed, so you don't have to recompute the whole aggregation again. I have a 3-level blog post, like an article about how to do MapReduce properly. And when we started implemented RavenDB MapReduce in 2010, we followed that, and that worked great until some guy put the US Census data into RavenDB. So US Census data is 310 million documents. And the MapReduce that he wrote was, okay, give me how many people do I have per state. And it mostly worked fine. And then we had California. California has, I think, 40, 50 million people. And the problem was that he created the index. I'm talking to you, by the way, about things that happened in 2010, 2011. He created an index and then started writing the documents. And at some point, he started writing the people in California. So for every document that he wrote, we would re-index the 40 million people in California. That caused us problems, so we moved to something more efficient for large things like that, called the multi-step reduce. Multi-step reduce effectively allowed us to split the number of people to California. Instead of whenever you modify, whenever you add something to California, you had to recompute the 40 million items. Then we would compute 1,000, 1,000, and 1,000, so about 3,000 items would be required to recompute, and that was done in batches and were very efficient. And there's a whole bunch of heuristics around what you touch and what you don't touch, and how you pull the data from this to do that, and a whole bunch of really, really, really complex stuff. And most of the code in the MapReduce is actually dealing with how do we structure the data on this, how do we pull the relevant data on this, and it's complex. Again, we keep repeating to the fact that over time we added more and more smarts to the engine, but the more smarts the engine have, the more complex it becomes to understand what it does. And then you look at a piece of code and you don't know what the heck am I looking at? Is this an optimization? Is this a scenario that we don't support any longer? So that makes touching the MapReduce code harder. This is what MapReduce looks like in 4.0. Effectively, we use the low-level Voron structure. I don't know if any of you are familiar with database theory, but we have the notion of a B+3. A B+3 handles things in pages, and in every page you have multiple entries. So effectively, what I'm going to do, I'm going to have for every, so in this case, we are showing, show me the number of orders per product ID. So in this case, I'm going to allocate a page per every product ID that I have, and I'm going to write all of the entries into that page. When that page is full, I'm going to split it and have 2 pages for this product ID, etc., etc. And I also going to have a parent page that reference all of the child pages for that product ID, and etc. And if I have even more pages, then I need to have 3 levels in my tree and things like that. What happened is that we can take advantage of that to handle the recomputation of the data. So here is the data for product 17. And you can see here that I have the entries for orders 1, orders 2, orders 3, and things like that. And then on the side, we keep track of how many entries of the total result that I have per each page. When something changes, let's say that this change, what do I need to do? I need to change this and recompute it. Once I've recomputed it, I need to recompute this guy. I can recompute this guy from the new value here and the values here for all of the child pages. And now that I've done that, I need to recompute this guy and from the new guy here and the cached value that I have here for page 13. So the whole idea is that we're able to reuse the structure of the B+3 to significantly optimize the cost of recomputing MapReduce operations. In fact, what happens if I just add a new order? If I add a new order, the following things happen. I add it here, and then I just recompute this, and recompute this, and don't need to touch anything else. I can just recompute the values here because MapReduce is cumulative. The end result is two things. A, we are much faster. And the amount of code that we have there is significantly reduced. Significantly reduced to the point where anyone can read it and understand that. Presumably, you need to understand what a B+3 is, but if you don't know that, then you're not working for me. And it's just a whole new world of being able to work with that. Just, I can't explain to you how significant the change in complexity is. Just amazing. How many of you use load documents in your systems? Load documents? Maybe it's you guys. How many problems have you run into from users with load document?
A lot.
Yeah, so a lot of issues. Load document is an amazing feature, but it has a problem that it can very easily be abused. Remember what I told you, that we made a decision, if it's painful, let's stop doing that? So load document is one of those things that is painful. So we changed the implementation of load document, and the core design goes something like this. What we are going to do, instead of touching the document whenever you touch one of the reference documents, and now if you have a document that is being referenced by 50,000 documents, then you're actually going to have to wait until we touch all of them. We're going to move that responsibility into the index. And when that responsibility is in the index, it's going to explicitly check on every indexing round, oh, did any of my load document change? And if there's, have any of my reference document changed? And if they have changed, I'm going to reindex the thing that referenced them. That's going to be on a per index basis. That's going to be highly optimized with regards to how it works. And it means that modifying a document that is being referenced by a lot of stuff is going to be extremely cheap. That doesn't invalidate all of the things that Dan talked about yesterday with the idea of don't have a single document referenced by the rest of your application and not keep updating that document. But it does mitigate a lot of the cost around that. And it also means that the only person who will suffer because of that is that specific index that is going to be that's going to have that load document inside it. It also means that we're going to very easily be able to point the finger. That's the reason this index is taking time, because of this load document issue. Okay, so WebSockets are relatively new, only been around for 4 or 5 years. We didn't have them when we started working with RavenDB, but having them now means that we have a much better alternative for certain scenarios. In particular, things like subscriptions, things like bulk insert, things like changes are all going to use WebSockets. Why is that? Let's consider the case of bulk insert. Bulk insert basically means something like this. Okay, I have a lot of documents, I'm just going to throw them at you as fast as possible. The problem here is that when we're using a standard HTTP, the behavior is request response. The server cannot respond to the client until the client send all of the information back. That causes issue when we have things like, oh, you try to write a document that already exists, that's an error. Or maybe you try to modify a versioned entity. Or any of whole bunch of stuff that can cause you an error. So at that point, we couldn't actually send that error to the client, because he sent us the second document in the 10 million that it's going to load. So we have to have another channel where the bulk insert open one request to write the documents to the server, and a separate request to read the response throughout. That was complex, that was annoying to manage on the server side, because you have two requests that you need to balance and understand and everything. And for fun, one of them can fail transparently to the other. But we moved all of that into Websockets, and now we have a much better way of actually handling that. It also means that the number of HTTP requests we are doing is reduced. Authentication is another good example there, where we have one TCP connection going back and forth for 3 round trip to do that, instead of multiple HTTP connections. And the programming model is much, much simplified, because instead of having to correlate multiple concurrent requests, I can just have a single stateful operation that, okay, write to the client, wait for a response, read the response, do something, write to the client, etc. Much simpler. So that's the idea with authentication. We currently have just API keys. We are currently considering whatever we want to support additional things, such as Windows authentication and certificates. I would appreciate your feedback afterward. For the most part, I really don't want to avoid using Windows authentication. I really want to avoid having to use anything except API keys, because we control API keys, and I can tell you what's going on. We currently have an open support request with a customer where they can't use Windows authentication because their domain controller is set up in such a way that I can authenticate whatever user is there or not. I cannot test whatever the user is an admin or not because of the permission on their ADAP directory. And as you can imagine, that means that it's a lot of fun to try to figure that one out. So we want to, again, centralize as much as possible into this. So that's bulk insert. That's actually really interesting. The current numbers that we have for bulk insert is about 50,000 documents per second sustained. We're talking here about multi-kilobyte documents. And we are doing that in several fashions. One of them is that we do large part of the work on the client side. So given an entity, on the client side, we transform that into the blit-able format, so there is no parsing cost on the server side. We also do a really cool trick. RavenDB is transactional, ACID transaction. If the data is, if I told you the data is there, you have to shoot the server to get data loss. But certain operations in RavenDB are not defined to be ACID until they are completed. So things like bulk insert, patching, update by index, or delete by index, are all operations that are not defined to be ACID. If you interrupt them midway for any reason, we say that some of the information might have been changed, some of them may have not. When the operation is completed, we guarantee that everything happened, and this is absolutely durable. So we took advantage of this behavior to implement lazy transactions. Lazy transaction means that we do all of the work around writing to the disk, but we don't actually flash to the disk. And that means that we wait for we wait until we have much larger amount of data pending, and only then will we actually write to the disk. That means that the IO requests that we send tend to be much bigger, which is much, much more efficient. When we complete the bulk request operation, we're actually forcing a flash on the journal file, and that's when we actually commit the overall thing. That's when we actually make sure that the entire operation is durable. So lazy transaction maintain the atomic consistent and isolated properties. They do not maintain the durability property. They do maintain, but when you finalize the centralized operation, then you run a final transaction that makes sure that the entire thing is durable. Note that if you have a lazy transaction in the system and you reboot midway, that transaction is atomically lost, which makes sense because bulk insert has that promise anyway. And the performance improvement is really, really nice. In the cars that I gave you, you have the design documents on the new replication model. It's going to be based on change vectors and WebSockets. That gives us some really interesting behavior. A WebSocket is effectively TCP connection. And a TCP connection has a really interesting property. It's ordered and reliable. It's reliable in the sense that if I sent you packet number 2 and you got packet number 2, then you got all of the previous packets. One packet, but still. Why is this important? It means that once I sent you a piece of information on a TCP socket, as long as that TCP socket is open, I can assume that you got that information. And that sounds like something very small, right? Why do I care if I can assume that you got this information? But it's actually really important because this allows me to avoid keep asking you, what is the last e-tag that you have for me? Because right now, whenever I'm issuing a replication request, I have to first, what is the last e-tag that you have for me, and then send you whatever I have. It also means that I have a much better idea of my topology, because I know that if this TCP socket is alive, then that other side is probably also alive. That means that we have much better handling for large clusters. And effectively what happened is that the replication algorithm in 4.0 is effectively based on gossip. If you care for that, it's a derivative of the plum trees algorithm. The paper is called Epidemic Broadcast Trees, if I remember correctly. It's a really interesting one. So we also use something called a change vector. If you now look at the metadata of documents in replication, you see that they have this notion of history inside of them. In 3.5, we've actually been able to reduce the size of the replication history to just the relevant things. In 4.0, we have moved to an explicit change vector. So and that means that we are able to consistently tell whatever two versions of a document are following one another or in conflict with one another. And we're also able to tell, based on just the change vector, what else do we need to see from any node in the cluster. That's very important for doing things like high availability subscription. That's very important for doing things such as, okay, the last server I talked to told me that his state was X, and that's the server-wide change vector. What I want you to do, I want you to tell me what is the, I want you to tell me whatever you're as up to date as the last server I talked to, which is important for certain distributed scenarios on high-value targets. Okay, another thing that we're doing is we move a lot more responsibility from the client side to the server side. What do I mean by that? For example, when you ask wait for non-stale result, that operation is actually handled on the client side. We currently have official clients for .NET, JVM, and Python, and we're working on having even more of them. And that means that we want to make the client as lean as possible. It also means, especially with regards to the kind of architecture that we have now with the indexes, is that we have much easier time making those kind of guarantees. Because now on the server side, we can say, okay, I have this index, I have a query on this index, I need it to wait until that index is non-stale. So I can just tie that into the indexing thread and have that notify me when this happens. Same thing for write assurance and replication over the cluster. One of the things that we intend to do, we also intend to add a flag that gives you the opportunity to modify the save changes behavior. And the save changes behavior basically means that you could say, okay, on the server side, I want you to wait until this information has been replicated to at least 2 other servers. And on the server side, I want you to wait until this information has been indexed by all of the relevant indexes in this transaction. The idea here is that we are making more explicit choices about when and how to wait. I mentioned performance and some numbers. Unfortunately, we are the RC2 caught us somewhat by surprise with regards to our current state, so I can't give you updated numbers. Last thing that we checked was 130,000 requests per second, and the limiting factor was actually our network bandwidth. We actually set up a couple of high-end EC2 machines and try to see what happened when we test between them. We run into a problem because the Linux kernel is set up to do things that are unoptimized for high throughput in many cases, which would mean that we have to change a whole bunch of configuration in the kernel. So that's going to wait until a few more months when we have something more solid. Just to give you some ideas, this is stupid, honestly. Routing. A routing of a request is something that you don't really think about as something costly. But when we run our profiling, we notice that actually deciding which piece of code gets to execute on which request tends to be quite expensive. Just to give you some ideas, we're using a data structure called tray, and the property of a tray is that we can find the relevant information in OW time, where OW is the length of the key that we are searching. Just to give you some idea, how many of you think that a better alternative here would be just to use a dictionary, right? What's the cost of using a dictionary? 01, right? So 01 versus OW seems stupid not to do that. Except that the actual cost in the dictionary, when you actually measure that, is not 01. Is the minimum of O2W. What do you mean by that? The first thing that you need to do in a hash table is to hash the value. So that means that you have to iterate over the key that you're doing. Now, when you found the actual item in the hash table, you need to compare the keys to make sure that you don't have a hash collision. Then you have to go over the value again. So we are actually dramatically faster than using dictionaries. There's actually another issue here which relates to the way that we place things in memory. And we are able to get much higher memory locality for the kind of thing that we're doing. And that gives us, last time that I checked, we were about, on a different machine, Web API was able to do 50,000 requests a second. We were able to do 80,000 requests a second. Yeah. Sorry, 50,000 requests versus 80,000 requests. We also tested that with Nancy, and Nancy was able to do 20,000 requests a second. Now, this is when you have one route. One. I think that on 3.0, RavenDB has over 400. Fun fact about the MVC routing, it's an ON operation. The more routes you have, the more costly it is. So that's something like that. Now, I mentioned that blit-able is much, much cheaper to work. So what you have here is the indexing time, including parsing cost, for indexing 18,001 kilobyte documents. So with JSON, that's 1.8 seconds. With blit-able, that's 22 milliseconds. That's the kind of thing that we want to see across the board. And for the most part, I think we're good at that. So we have software that runs on Linux. You saw that we have the ability to write to RavenDB. We have the ability to create indexes. We have MapReduce. We have the auto MapReduce stuff that we have. So that's amazing, but we still have really lots of stuff to do. One of the things that we are doing is we want to update the client and the studio. So the client API deserves a lot of love. Effectively, what we want to do, we want to say, okay, everything we have done on the server side, we want to go and look at everything we're doing on the client side and see if this makes sense. Can we do this better? Can we do this much better? And probably we can. We are going to have a UX team go over the studio, both to see what we can improve, and we're probably going to move to more task/wizard-based stuff to guide people toward features. One of the items of feedbacks that I got yesterday was that if you know what you're doing, you can find everything that you do. If you don't know what you're doing, you have no way of finding where this is at. We're also probably going to have a designer go and redo the website, the studio, just to make sure that it's look modern, works on phone and browser resolution, stuff like that. We have a whole bunch of bundles that we still need to do. We have a lot of performance work. Just to give you some idea, the schedule for working on 4.0 include about 2 months where the only thing that the entire team is going to do is sit on the profiler and go over all of the hotspots and fix them. Obviously, we have stability issues. We're running on the CoreCLR, so that's something that we have to wait until that's going to happen, and we still have a lot of performance work to do. Notice, by the way, the reason that performance is here so often is that this is literally the schedule that we have. And that's the kind of importance that we give to this. And that's roughly the schedule. So by the end of the year, we're going to have a public preview. That means that you can take it, play with that, see what we're going to do. Something around March, we are going to have a beta. About a year from now, we have the release candidate, and just over a year from now, we're going to have the RTM. It's important to understand that in order to make those kind of changes, we are going to break things. So, for example, upgrading from 3.5 to 4.0 is going to be something that you do through the smuggler. What will effectively happen, by the way, is that you don't care. But we'll have a tool that says, okay, let's upgrade those servers, and it just does it for you. But we're going to make some client API changes. Most of them are going to be at the edge cases and are going to be a clear upgrade path for that. But that's something that we made a conscious decision. In order to make those kind of choices, we have to be able to actually break things to get that level of performance and changes that we have. And now's the time for questions. And do you have the mic? The mic to give to people? Yes. So, questions? Yeah. 1 second. Check. Yeah. Dan over there.
I was just wondering with the tree-based routing and the trie-based routing,
yeah.
If that's significantly better than the dictionary, why give web API to use that? Is there a reason?
NancyFX is using a tree-based routing. we are 4 or 5 times faster. I wrote a blog post about the implementation and the design decisions that you can look at. The routing for the tree-based routing for RavenDB is very, very specific to what we're doing. For example, we cannot handle Unicode characters in a route. We can't have, so example, you can have a database name or a document name that contains Unicode characters, but in the route it would show up as a parameter. The actual route, so databases /doc/stats, something like that, that all has to be ASCII. The reason it has to be ASCII is because we use that to populate an array and index directly into that array and a whole bunch of other performance optimizations. That's probably not suitable for something like a MVC, where you actually want to have the route contain Unicode characters. At least that's what I assume. The non-CFX implementation is just bad stuff going on there. Yeah, more questions?
You talked about the indexing per collection.
Yeah.
How does that affect multi-map?
It doesn't. So multi-map indexes effectively now, in every indexing run, you're going to do, okay, for each collection that I'm indexing, give me everything from that collection that I haven't seen, and that's it, and index that, and then for the next collection, the next collection, next collection. So effectively, you don't care. It's the same behavior for a multi-map. There is some complexity internally that we need to store multiple e-tags for the same collection, but that was solved, and that's not an issue.
Okay. One other question. The map reduce, is there any thoughts about multi-map reduce now that you have these changes for map reduce?
We have multi-map reduce. So you can have multiple maps that are reduced to the same thing. You're talking about multi-reduce.
Yeah, multi-reduce.
Yes. So that's something that we want to look at. The problem here is that what you typically want, you want to have not so, okay, let me try to explain. The problem here is that what you typically want to do, you want to chain reduces together, and that's something that we can look at. The problem is how do you explain that to the user when I'm actually working on this index? Which of the reduces do I want to handle? And there's a lot of complexity, not in the actual implementation, but in the actual API and usage. So that's something that we need to look at whatever it makes sense or whatever it's going to be a really confusing feature. More questions?
You mentioned about the lazy transactions on loop insert.
Mm-hmm.
Are you planning to leverage that on things like delete by index and similar operations?
Yes. So anything that doesn't have actual consistency guarantees, so all of the bulk operations that we have are going to use the same feature. For the same reason, because we already now guarantee that only at the end will you know whether this was successful or not. And it's okay for us to say, okay, midway through we had an error, and we can accept that some of the things happen and then you had an error. That's a very important property for us to be able to use lazy transactions, and that's actually true for update by index, delete by index, and back insert. I don't think we have anything else that can do that, but those three I know that we are doing this.
Thank you. I have another question. Do you have any plans to have the concept of right concern similar to what we have in Mongo?
That's right assurance, yes. We have it right now. One of the things that we're going to do in Voron is move it to the server side. So right now, this is a feature that you can use. It's just that this is one of the concerns that are currently on the client side, and we want to move it to the server side because that makes more sense for having more clients.
Okay, so right now is it possible to have like don't need to wait for the transaction to commit, but I want to wait for the server to receive it. So that would be the right concern 0 of Mongo.
Yeah, that's something very different. What you want to do, so that relates to how they're processing transaction. I think that's stupid. Because what they're effectively saying is that, oh, I will accept the transaction, I will accept the write. I'm not going to tell you if this is going to be successful or not. I'm just going to tell you that this was sent to n number of servers. Honestly, I think that's insane. Because that means that you got the write, you don't know if it was successful or not. If you have a unique name conflict, for example, it's going to fail after you got the, yeah, I got this. For me, this is data corruption. So that's not going to be the case for RavenDB. What you have is the case that this was actually committed on n number of servers. This is what we have now.
Okay, thank you.
I have a couple of questions about upgrade. First question is, when you upgrade the database from 3.5 or 3.0 to 4.0, is that include the index upgrade, replication upgrade, everything?
We are about a year away from the actual implementation, so anything that I tell you about upgrades is suspect. Index upgrades, we will probably require to do. Index update will require indexing. Replication upgrade, we will not be able to replicate between different versions. So 3.5 couldn't replicate to 4, and 4 couldn't replicate to 3.5. Yeah.
How about the client side? What's the level of effort of our code, our applications code?
There shouldn't be much. Again, for the most part, just to give you some idea, we have about 5,000 unit tests that we are porting to Raven 4.0. And for the most part, I don't want to touch all of that code. And I'm sure that anyone who has a non-trivial RavenDB application doesn't want to, oh, we upgrade the code, let's go and change query to query 2 because they thought it was better. For the most part, the session API is going to remain roughly the same. Roughly the same means that you would need to recompile the code. You wouldn't need to rewrite the code. The stuff that isn't on the session is likely to have more changes. So one of the things that we want to do, we want to change the way we do JSON serialization. So if you do create serializer, that will need to change. But we feel confident that this is okay to do because those things tend to be in one location in the project. So you can change it in one go. It's not that you have to go to every controller in a big system and change things. Absolutely, yes. I'm sorry, can you raise your voice? Yeah.
For 4.0, you said since it has the auto index, so you don't, do you recommend, or it doesn't have this predefined index feature in there?
I'm not sure that I'm following. Static indexes are there and they exist. They're still valid use case for doing them. They're just much rarer. For example, you would want to use static indexes if you want to do a full text search. You want to do static indexes if you want to do spatial queries. You want to do static indexes if you want to do order indexes. So I want to be able to search on multiple fields at the same time. You want to do that if you have complex map reduce requirements, those kind of things. This just means that the static indexes are going to be for the more unique scenarios. Even today, we have people that develop full-blown RavenDB application. They never create a single static index. Just let RavenDB handle all of that for them. That's not necessarily a good thing in some cases, but it works. And we want to make sure that let's just let RavenDB handle everything is a scenario that is much broader. Okay. And we have, I'm already 20 minutes overboard, so one more question and then we're done. If you have any more question afterward, feel free to catch me and we'll be happy to answer anything.
Actually, I have two questions. First question is, look like you're trying to have some schema information, look like because you have the pointer stuff to try to locate,
The blit-able format contains, okay, so we actually have two options and we haven't decided yet on which one we'll use. The blit-able format contains the structure of the document itself. It just contains that in a way that is much more efficient for us to use. So if you look at the blit-able object and you have a name field, you will have the name string inside that byte array. The other option is to do something called properties lifting. And in many cases, if you have a single, if you have collections that all of them have the same name property, we don't necessarily have to store the name property string in any one of them. So we actually wrote the code to handle that. The problem is that we also need to handle versioning of that. So if you have dynamic data, if you have an entity that have multiple different property sets based on version 1, version 2, version 3, that needs to be handled. Right now, we store all of the property inside the object itself. We have a solution for doing properties lifting, but that still need more testing to see if we're going to implement that or not.
I think that's a very good feature, actually. Will address a lot of problems. But I believe we also have some other overhead because you store pointer all this information again.
I can't hear what you're saying. You have to raise a voice.
Okay. I think have this kind of schema or mapping information actually have a lot of usage.
Schema doesn't make sense for use cases. What you're talking about is if we do properties lifting, then we are very close to the point where we just need to store the offsets for each property to how you would store things in a schema-based data store. The major difference is that we store offsets for everything, and they can skip offset storage for fixed-sized fields. It doesn't actually matter. Even on very large scale system, it is not an expensive thing to do. It used to be the case that you care about every bit and byte, but if I tell you that in my 100 million database, then the overhead of the metadata is, a gigabyte, you're going to say, oh, that's a lot, but the actual database is 2 terabytes, you don't care. Yeah. What was? You have to put the microphone, otherwise I can't hear you.
This is more like similar approach related to handle actually their table level storage.
Yeah, so so the idea here is that we're going to do those kind of optimization like property liftings and stuff like that, but we can do that without impacting the external behavior of the database. So from your perspective, we're using less space, we're more efficient, we can. One of the things that we do in the blit-able format is we store the properties in lexical order. So when you query on the properties, we can find them by just doing a binary search on the property names. That means that doing a property search in O log n operation. What we have done is we realized that, here is an optimization that we can do by remembering the position of the property. We can start from there, and now the cost of finding a property name for the first time is O log n. The second time that you search for this property, the cost is O1. And that's the kind of optimization that we can apply without having any external difference, and it's make a lot of change to the actual course that you have. And that's the kind of thing that we want to do.
Yeah, it's good thing. And that's another question is, what is your dream when you try to post to the Linux platform?
I'm not sure I understand the question. What is?
You guys try to post to the Linux, right? What is your dreaming? Do you have technical dream or business dreaming?
Why do I want to run on Linux? That's the question.
Yeah.
I want to run on Linux because users tells me that they want to run on Linux because it's across the board is cheaper to do so, because I get to run on hardware like this and I get to run on monster machines, because in certain markets then not running on Linux is a major problem. In South America, in Russia, we got customers that says, I would really like to use you. I cannot have Windows in my data center because I'm looking at being able to deliver you a RavenDB Docker image that you can plug in and start running, and that makes things much simpler. So mostly the reason why I want to run on Linux is that customer wants to do that. There is economical reason to do that, and it makes deployment easier. And it also means that at the end of the game, I can literally ship you a machine. It may be a Raspberry Pi with RavenDB, or it can be a pizza box server, and it just happens.
Because I think I understand your code base made like a .NET, C# right?
Yeah.
Does that make sense of running on the Linux?
Yes.
Okay.
Yes, it does. Okay. Guys, thank you very much. If you have any question, come to me afterward.